Okay. Wait a minute. What I did? Okay, it's terminated. Okay. So over the break, I have received some excellent question, which I feel it might be better for us to kind of talk about this question. The first question is about why. I mentioned at the end of let me see. Am I recording? Okay. So at the end of the last lecture, I mentioned that in this memory address, virtual memory address, there's a one portion I basically reserve for the kernel. So typically for 32-bit computer, I never check for a 64-bit computer exactly how much bigger memory virtually, but in 32-bit computer, the virtual address is 2 to the 32, which is 4 GB. And I gave the top 1 GB to kernel. And then the rest of the 3 GB was given to supporting the execution of your program for every single program. So every program got 4 GB. So the question was, why do I need to give kernel 1 GB? So let me use this example. I kind of skip it when I first talk about this, but now I feel since you guys are asking this excellent question, so I leverage that to talk about that. Remember I said I have the system call interface, which provide a boundary about what we call operating system kernel, and we talk about the user space. So let me, for example, give you an example. When you're editing your email, I was using this example, editing your email. So you basically using your whatever editor, you start typing character, editing your device. Oh, sorry, editing your text. Eventually, you want to send this email into the internet to deliver your email. So you have a program which is editing. That email is in user space, but eventually you need to send it out. Okay, I'm just simplifying the example. I'm using this only when you're sending. This is a system call. Because when you want to send the email, you're going to send it through the kernel, because the kernel has network protocol. You want to send out, that's going to involve some kind of network protocol related issue. So it has to use the kernel service. But on the other hand, when I send the email, I must have the email itself. Where's the email itself? The text is in the user space. But what's the program to send that email? That's in the kernel. Okay, so you can think about, oh, wait a minute. Now I need to execute the kernel because it's a kernel mode, and the kernel need to access the memory in my user space. So then you can complete. So you can see that the relationship between kernel and the user space is very interesting. Sometimes it's a kernel service, but it needs to access your information in the user space. Okay, by the way, this is a very advanced concept. I don't expect you understand the first time, but this is an important concept for understand the most important structure about operating system kernel. So operating system kernel is supporting 770 processes simultaneously, and this kernel is very critical. If this kernel fails, then the airplane will crash immediately. So that's why this part we have to protect it. We have to protect it, meaning that while we are sharing information, but I want to make sure I'm doing in a way such that I can clearly separate what's user, which user could be you download a program from internet, might be contain mistake, error, or virus. But then with the kernel, which is a serving for all the applications, so we need to have a boundary to separate. So remember, this is called system call interface here. And remember I said trap into the kernel. I never explained what it is. Let me actually now explain what do I mean by trap into the kernel. Meaning that when you have a process, when you want to make a system call, you're not just calling it. You really just give the whole thing, throw it into the kernel space. So basically now your user process during the execution of the network protocol, the whole memory space is being controlled by the kernel. And the mechanism to do this control from the user space to kernel is using a concept called software trap. So software trap is a mechanism, it's like a hardware interrupt, but software trap is basically generated by the user program say, hey, I want to send a trap and let the kernel take care of the process. So now the process is being delivered to the kernel. So the kernel is using this space to retrieve your email in text and using its own code of network protocol and send it out. Okay, so in this process, you can see that the kernel sometimes need to touch your data, not sometimes, a lot of time. And therefore, you need to have the same memory space. You want to avoid, by the way, copying. The easiest way, by the way, there's another important operating system consideration. We want to avoid copying. Whenever you do memory copying, it wastes a lot of time. So we want to say, hey, you just give me the control of the whole memory map, and I will do everything on your computer. You have to trust me. So essentially, kernel always have privilege to access the user data. And the user never have a privilege to access kernel data. When the user trying to access the kernel data or trying to access something which is not supposed to happen, is called segmentation fault. Because you're trying to access something you're not supposed to. Okay, so now I hope that answered the first question about this map, that why I need to have a 1 gigabyte of memory on top of here. What was your question? Second question. Okay, all right. The second question is, why do we need such a big memory and how do we do the mapping? Okay, I'm going to answer very briefly. Because virtual memory is big, the requirement of application program vary. Some program needs a lot of memory, some program needs little memory. In order to easily allocate memory to each of the application program, I see that virtually I have a 16 exabyte. I can just very loosely allocate here and there, because no matter how I do, I'm not going to use all 16 exabyte. You actually think about, in the virtual memory address 64-bit, especially sometimes we call sparse memory model, meaning that the whole 16 exabyte, the portion I'm really allocating for application program is very small, a very small percentage, but it can handle almost all kind of application. Okay, but later I will show you an example. You will see what's happening. Okay, all right. So now this is a memory map. You have your kernel over here, and now let me actually tell you there are two parts of information. Let me first explain this part. See, this part is what we call a.out. Your executable file is over here, and inside your program you have something we call text. Text is what we call your program, your executable program itself. And you have some initialized data. And these two are mapped to the lowest memory address. Lowest memory address in the virtual memory address. And then I'm not going to talk about like ARGV, ARGC. Okay, those things are small thing. I'm not going to talk about that. But I'm going to talk about two things. It's called user stack and talk about heap. User stack and heap. So when you're calling a function, you're actually going to put it on the user stack. But when you do dynamic memory allocation, like you use malloc and free, you're using heap. So there's one region of memory that's related to user stack. There's one region of memory related to your dynamic memory allocation. And then I have your program is coming in over here, your initialized data here. So that's a very quick virtual memory address allocation related to your program. Okay, there was a bunch of interesting questions from this way of allocating. Okay. Let me first, if you look at the map, look at this number. I said this is the lowest memory address, right? This is the lowest memory address. What do you think in your mind? What's the smallest memory address that you could have on your virtual memory or main memory? What's the smallest memory address? Chocolate? It's called chocolate address? No, it's called 0, right? All 0. If you have a 0, 0, 0, by the way, this is 32-bit computer. That's why it's only have an A. But it should be more than 8 has decimal digits. 32-bit, I should have. Yeah, 8-bit. Yeah, sorry. I was wrong. Yeah, 8 has decimal digit. Each digit is 4-bit. So that's why 8 times 4, that's actually 30. So what should be the lowest memory address? It should be all 0, right? 0, 0, 0, 0, 0, 0, 0, 0. That's the smallest memory address. Remember, you guys are a programmer. The smallest number is always 0, not 1, okay? The smallest is always 0. But why this address is not 0, 0, 0, 0, 1, 0, 0, 0? You want to give a guess?
Safety.
For safety, exactly. It's for safety because in Unix operating system, the first page. So the way we handle memory is that all the memory, I said I have a 2 to the 32, 4 GB memory, but I separate the memory into page. Each page is 1 kilobyte. Each page is 1 kilobyte. So essentially in the virtual memory, I skip the first page. I skip the first 1024 bytes. Okay, so if this is the main memory, then you're saying you're wasting 1 kilobyte of memory. But this is a virtual. This is a virtual, so I'm not losing anything. I'm just skip my memory allocation in the first page. Okay, why is that? Because the designer of C programmer knows that the most commonly mistake made by C programmer is they forgot to allocate memory. All right, so let me write a small program to show you what's happening. So remember I said I want you to experience segmentation fault. So now I want to use the program to show you how you can generate segmentation fault very easily. I would just use my previous example. So I'm going to block this code. Okay, I'm writing a very simple program, only 2 lines. The first line, I define a variable called XYZ PTR. The type is a pointer to an integer. And the second line, I'm just printing the content of that integer. The content of that integer, which is XYZ PTR. So I basically just print out a integer through a pointer. I never allocate memory. Okay, if I run this program, okay, I'm getting a segmentation fault. Why is that? Because I'm trying to access the memory I never allocate. And guess what? By default, if you have a pointer, you never allocate memory, that variable, that the pointer, the value most likely is happen to be zero, all zero, the smallest address. So this particular design memory map is intentionally designed in an operating system virtual memory is basically saying that you're not supposed to access any memory address that's actually in the first page of your first virtual page. By the way, later, if you have a chance to take operating system, usually we say the virtual memory, each 1K is, we call it page, but in main memory, we'll call it frame. So sometimes we call it virtual memory page, physical memory frame. Okay, they were the same concept but at a different level. So virtual memory address, essentially I'm wasting 1K of virtually addressable memory, but that's okay. It's not real memory. I'm not wasting my real memory. I'm just wasting a allocation. I mean, I have a 16 exabyte. I don't care about 1K, to be honest with you. So that's why it's a reserve, but it helps us to trap a lot of segmentation fault. By the way, this was designed for 30, 40 years. Whenever you have a virtual memory, you have this design to help programmer to quickly realize that you have this runtime error. But this is there is another issue which is quite interesting. I want to say from this example. In the segmentation fault, that sometimes you try to access memory here. Of course, the segmentation fault, but sometimes there are certain other region you might also have segmentation fault. Okay, so there are different kind of checking. If you access the kernel, definitely that's a memory fault. But some of this area, you might actually get into that as well. Later, if we have a chance, we will talk about that. Okay, any question at this moment? So hopefully now you understand that, okay, why I started with 0001000 because I skipped the first page in virtually. And now the rest of the class, I'm going to talk about the heap and the stack. Okay, I'm going to talk about heap and stack. I want to come back here to ask you another question. So as a C programmer, I want to ask you this question. There are some variable I call local variable. And there are some memory which is being allocated via a library function called malloc. In this map, I told you, if you want to do malloc, you're going to allocate memory. Okay, now I know the real question I want to ask. This is another very critical difference between Python programmer and the C programmer. In Python programmer, in their mind, they don't have this map. But C programmer, you should. So in other words, I'm telling you that there's a region called heap, which is a regional memory. Whenever you use malloc and free in C++, when you use the command new and delete, later we'll touch that, is also in the heap. So new and delete is C++ version of malloc and free. Okay, so when you allocate that memory, when you say, okay, this is the memory that you create through heap, that's actually over here. And then when you define what we call a local variable, what's the definition of a local variable? Let me show you the example. Let's go back to my GitHub. Let's use stack. Using this example, you see that I have a function called bus over here in line number 6, and I actually inside this function I declare an integer called zx. This is a local variable because this variable was declared inside the scope of a function that's locally to this function bus. So this is called local variable. Okay, so now so that's why C program, you need to know whether it's a local variable or it's a malloc. But now I want to go back to this slide. Okay, what I'm going to teach you right now is a really important concept for C programmers, so you avoid a lot of mistake. I have seen so many programmers, they make the mistake because the concept of a memory map is unclear. So remember, I have a function called zx. That's a local variable. It's not being malloc. It was just declared inside the function. Where in this memory map do you think I will store that zx? Because whenever you have an integer, you have object, you have whatever, it must somehow be alloc on this memory map, right? Where do you think that will go? It's actually on the stack, the user stack. So if it's dynamically allocated using malloc or new, it's going to be on the heap. But if it's a local variable, it's going to be on the user stack. I don't believe at this point from the first semester you learned about user stack. You probably heard about this, but you never. So I think this is kind of very advanced concept, but it's important when you touch an operating system to talk about what is a user stack. I'm going to show you a program to see how this. We have to learn. Oh, the other thing I want to tell you before I skip to that. You see this arrow? So there's a direction about the memory growth. So the memory growth is basically say heap. When you're using more memory, you're using the memory address from the lower memory address to a higher memory address. Remember, this is the lowest memory address allowable to Unix processes, which is skip the first page. It grows this way, and the kernel is using the top 25% under 32-bit computer. So when you allocate more memory, you actually go up. The memory go up, address go up, meaning that you're using more memory, you're supposed to see higher memory address. And user stack is on the other direction. It goes down. So it goes down, so it means that you're using more memory on the user stack, and it's actually supposed to go lower memory address. So it's from higher memory address to a lower memory. So it's a reverse stack. If you learn data structure later, you will hear the concept stack, but don't worry about that now. I mean, initially what they were thinking is that they want to kind of let two regions of memory that grow bump into each other, and the share library in some system, they put it in the middle. If you want to have some kind of share library, you put it in the middle. And that's okay. Historically, there are some reasons which I don't want to cover, but higher to lower and lower to higher. So now we're going to see. I want to tell you what is stack. What it is using this program. I'm going to use this program called stack, and the stack has this main program. The main program is the entrance of your program is actually going to call foo. And then the foo is defined over here. The foo is going to call another function called bar. And the bar is here. And the bar is going to call another function called bus. And the bus was a function I talked about earlier that's contained the local variable zx. Okay, so I'm going to draw it via a PowerPoint slide to tell you what is a stack. So it's main. Down. This is going to be mistake. What I want is Our line is this, I hope. Okay, I have a main. Let me make it a little bit bigger so you can see what's going on. So main is going to call let me make it bigger. Let me do this. Let me make it bigger. Okay, main is going to call foo. And foo is going to call bar. And bar is going to call bus. And this is main is here. Okay, now I'm happy. Okay, so this is the calling stack for user. Oh, I have to do this. I want to change this to this way. Get rid of this part. And to do this part. Okay, now it's fine. Okay, so whenever you make a function call, your local variable, when you make a function call, the first function, of course, main. Main is going to have some local variable. And that local variable need have some memory, but that memory is on this regional memory on the stack that's allocated to main. When main is making a function call, main is going to call foo, then essentially this memory region, the local variable for foo, is actually going to be stacked over the main. So from the memory region is main and then foo, but the reason is not stack. Usually because why? Because the stack grow down from the high memory address to low memory address. That's why I draw it this way. Okay, so the local variable of main is over here. When you're calling foo, the local variable memory is on foo. And then when you call bar, it's actually on bar. So you have a main's local variable, foo's local variable, bar's local variable available. And then when you call bus, it is going like this. So you stack all function call. Okay, and when you make another function call, you can imagine this can go really deep. Sometimes, remember, I easily test the functions, usually the level of 34 level. When you do, later we'll teach you how to do debugger. You will see a lot of function when you're calling, especially use standard library. The depths about your function, for example, you call printf. The printf will go deep into that. So it's going to be like a 34 level. But now I'm going to show you only 4 levels, which is easier. So each of the memory region, you have your local variable. So when you return, when your function bus return, is going to be popped. So this memory is gone. So you're actually come back to this particular status. So main called foo called bar, and then called bus. But then bus return, you go back to this, and then I'm going to call another function called printf. So when you have a printf, printf is going to be here. It's going to replace the bus, the memory, the same memory, because it always grows this direction going down. So this, basically the bus is gone. Not only gone, but it will be overwritten by another function you're going to call. So that's the property about the stack. So when you make a function call, there are two information need to store in each of this, what we call region. We sometimes call the friend area for each of the function call. It store a local variable. It also store the return address. Because whenever you're done with the bus, it needs to know where do I go to go back to the previous function and where do I SQ from the remaining of the previous function in this case is bar. All right. So one thing I want to tell you, the main difference between heap, which is the malloc, and local variable is that local variable, when you are done with this function, the local variable is not guaranteed to still be there. It's on the stack, but your next function is override. So if you define anything that's local variable, it's supposed to just that function and it's gone. And this is like a very commonly made mistake by C programmer when they're not clear about the situation. They create some local variable over here. They create a local variable, and what they did is they passed the pointer of the local variable using a concept called call by reference to another parameter and return to bar. So in the bar, you cannot access to bars, but you actually access to the pointer to that local variable, and you try to use that pointer to dereference. And obviously, the result is logically wrong because that portion of the information has been probably reused by other function. So if you want to have something more permanent, you should use dynamic memory allocation because there are two regions of the memory. One is called user stack. One is called heap. And user stack grow this way, and the heap grow this way. Okay. And any question about the difference? By the way, I want to ask you, have you learned the concept about local variable before the first quarter? Local variable? Maybe they use a Chinese name. Some of you nod your head, so it's probably there. Local variable is gone when you exit the function. Not just the variable is gone, the memory region is gone as well. Okay. All right. Now let me show you write the program to actually validate the concept I just mentioned, just talk about. So first I will do heap. Heap is easier. Okay. I do have heap. So inside the heap, this is what I did. Okay, I'm writing this piece of program over here. Just look at this piece. Okay, what I did is I have a pointer called XYZ, which is pointer. And over here, I actually malloc a piece of memory, which I call the size of memory I allocate is called alloc size. I will explain that a little bit later. And then the function, I assume you have used a malloc before. So when you do malloc, you actually go to the heap to say, hey, you give me one piece of memory that's at least the size of this alloc size. I put it here as a parameter, and you return the address or the pointer of the first byte of that chunk of memory that from heap. So let me tell you what is malloc. Malloc saying that, hey, I want you to give me at least this amount of memory. So the heap is going to find out any pieces they still have. That's actually bigger, the same or bigger than whatever you allocate. And then they will give you the heap malloc will give you the memory address of the first byte of that chunk. Okay, so that's the XYZ. And then what I do is that I print out, okay, what's the chunk size I just allocate, and what's the address of the first byte. Okay, this is what I did. And then what I did is I did this 8 times, but each of the time I actually allocate more. That's why the first 2 lines, the first line over here is doing this alloc size of character times 1024 1K times power 2. Okay, so that's, I kind of allocate 1K, 2K, 4K, 8K, 8 times. So let me try to run this program very quickly. Okay, I run this program and I print this A line. So let's take a look at a few things. First, I want to tell you the chunk size I allocate 1K. The second time I allocate 2K, 4K, 8K, 16K, 32K, 64K, and then 128K. Okay, I basically allocate. But then look at the memory address of the first byte of each of the chunk. You see that the address is increasing. The first allocation is 9200 as 9600, 9E00, 8E00. So the memory, in fact, grow up. The memory actually grow up. So you can see this is a consistent with this figure. Is consistent with this figure that the heap is actually going up in the memory address space. Okay. Later, there are some other issue about the heap management, but I don't think in EE1520 I should go that deep into the heap. But heap is a major piece of memory. Maybe when we talk about C++, I will talk about how is a C++ memory allocation somewhat different. But at this moment, at least you know there is a memory map and the heap go up. And whenever the function go out and in with the user stack is not going to override of the heap because I have clearly two regional memory in my virtual memory address. Okay. And the other thing now I remember from the programmer perspective, from the C programmer perspective, the memory address you print in your program is always a virtual address. It's not physical address. Okay. Later, I will tell you more about physical address, but now at this moment, we should all deal with the virtual address. You can see that the virtual address grow this way. Okay, any question about heap? Now I'm going to go stack. So the stack, I'm going to show you this picture that the main program is called foo, it's called bar, it's called the bus. And I'm going to print each of the address over here, and you will see that the address is actually decreasing instead of increasing. Okay, but how do you actually see when you make a function call? How do you know where's the memory address? So now I'm going back to the stack program. You can actually try to play with it a little bit. Okay, so I'm going to tell you a little bit about how I obtain the memory address on the stack. This is the main program. Let me first tell you the structure about the program. You see that this is the main program. Am I still recording? Yes, I'm still recording. I'm happy about that. Okay. Okay, so foo is going to call bar, the function bar. And the function bar is over here is going to call bus. And the bus finally bar, and then finally bus is this program over here. Okay, so you can see that. That's exactly what I show you on a PowerPoint slide. Man, and then call foo, and then call bar. A bus. Okay, man, foo, bar, bus. Okay, that sounds good. Okay, so I want to tell you this two line. This is a little bit you probably never learned about this. This is kind of advanced usage of C for you to understand the stack and the function. So the first part is I want to be able to retrieve what is my return address. Because remember, return address is something which when you finish this function, where you're going to return to the previous stack frame. So I have a way to actually see what's my return address. I mean, normally the application programmer, especially Python, you don't care. Okay, but C programmer, sometimes we can actually know what's the return address, so we can control, and especially for cybersecurity purpose, because your return address sometimes could be overwritten, or could be somebody actually maliciously try to modify, and such that you get what we call control flow hijack. Okay, that's another topic I'm not going to talk about right now. But you're using this built-in function called built-in return address, which should be available for any C compiler running on Unix operating system. This 0 means the level. 0 means the current level. 1 means the previous level. 2 means the previous level, something like that. So this will give me the return address, meaning that on my stack frame of this function main, what's the address? What's the address I store for the return address? This essentially gives you an idea about where you are in terms of this picture. This picture over here. So essentially, we're printing the return address inside this main region, okay? And then what I did, you see, I'm just doing a printf. I said, what's the return address of 0? What's %p? And then what's the function? So by the way, in C++ or C, if you say underscore underscore function or capital underscore underscore, this will give you the function name of the current function that you have. Okay, and that's in C++, you have another one which actually print not just function, but print the whole thing about the class and the other information. So that's kind of handy when you want to debug your program, you want to know where you are. So this basically say the function and the pointer of that particular stack frame. And then I want to tell you in the foo, I also do the same thing. And in the bar, I do not only return address 0, but I do return address 1, which means that I want to go up one level to my parent in the function call. And then finally, in the bus, I actually print 0, 1, and 2, which shows the address of the return address of all 3 stack frames over here. Okay, so I would say 0 is bus itself, 1 is bar, my previous one, and then 2 is going to be foo. Okay, so there's 3. Let me show you the program, show you the address, and then we can go back. This is probably very hard for a lot of you. I can completely understand. Okay, let me first show you how this runs. Okay, so I'm only going to show you this portion, this last few lines. Only show you this part. You see, I'm actually printing 0, 1, 2, and the function name is all bus. So these are basically those 3 lines of printf from the function bus. And remember I said level 0, that means it's for themselves. What's the address of the return address in bus, which is pointing to the bar. And then this one is actually in bar when pointing to foo. And this one is actually in foo when you're pointing to main. So essentially, what's the return address? If you go back to here, the calling stack frame is inside the bus. It has to have a pointer return to bar. And inside bar, it has to have a pointer return to foo. And then inside the foo, it has a pointer that point back to main. And the address I'm printing is the memory address on the stack to store that information. Those are not the return address, but it is the memory address on the stack to store that information. Okay, so that's the idea. So that's the allocation. So let's first take a look at their value. If you take a look at that value, the value in fact is decreasing. The memory address decreasing. The bus Okay, this one is for the third level, which is from the foo back to main, which is the top one, so it's the highest. And then this one is from the foo to bar, which is a smaller. This one is a 7F10. This one is decreasing, becomes 7EC0. And this one is even decreasing, become 7E48. So you can see that main actually has a higher memory address than, this part is in foo. So foo has a higher memory address than bar, and bar has a higher memory address than bus. Okay, so essentially what this is showing you is this picture is storing away is the value. Okay, the three-pointer is actually here. I want to show you this. And I get my stuff. Oh, where's my... Whenever I'm using how do you say that? Zoom, I kind of lost the... Okay, I'm going to do this. I cannot do this. That's very strange. Okay, I'm just using text in that case. Ah, I got it. So this ball represent the return address. So the three return address are the return address here, and return address here, and the return address here. So bus have a area of memory on the stack that store the memory, store the address that allow bus to return to bar. And bar has a memory address allow them to return to foo. And foo has also a memory area that's actually returned to main. So if I look at the three lines, I want to copy and paste from here. I'm here, so I can do Control C. I want to tell you what the relative memory address. Okay. So I have this three memory address. I want to tell you, give me a line. Ah, I got it. So the first line is actually this memory address over here. And the second line is pointing to the memory area over here. And the third line is actually pointing the memory to over here. Okay, so you can see that this three value, the three value on my program to access to the return address on my stack, they're actually going exactly in the opposite direction because this is the largest, which is 7F10, 7EC0, 7E48. You go back over there. Okay, so this is pretty much everything I need to tell you about memory layout, because now you actually see this picture, you understand where's the user stack, where's the heap, and where is the rest of the stuff, and where's the kernel. And this pretty much, you need to understand everything about memory allocation, because based on this, I can probably build everything you need. Later we talk about regardless C++ or GPU. And this concept, once you learn this is probably okay for the rest of the quarter, rest of the semester. Okay, any question? Chocolate? Anybody want chocolate? That's a question too, okay? I want chocolate. That's a question. You can get a chocolate without asking a question. Okay, so I will see you. Okay, by the way, I think that there's important. I'm actually flying to Washington, D.C. on Sunday. I won't be back until March 12th, March 11th. So we're going to have three classes. I'm going to do remote. So I will be like a midnight in Washington, D.C. Because I was sent by NSTC to have a meeting with NSF in US in Washington, D.C. So I will be doing this remote. Okay, so you will still see me. My TA will come here to present the computer. We'll still do Zoom. Okay, we will still have a class last week, but you will see me wearing pajama probably. Okay, in the hotel. All right, I'll see you. You have a good weekend.
这个 return address 是存那个 stack address。
等一下，好，先把它关掉。